Hello, my name is Dan Low. In this video, I'm going to talk about halting problem, and that is undecidable. So let's first introduce what is halting problem. So the halting problem basically we give the problem a name H. So given a program P and an input I, determine if the program holds on the input I. So this is the famous holding problem back in 1936. This problem was the first proved by Alan Mathison Turing. Okay, and this gentleman is also introduced Turing machines, and that is the classical theoretical computer science foundation, or somebody called Turing is the father of theoretical computer science. So now in the title we mentioned undecidable. So what does undecidable really mean? Okay, so basically if a problem is undecidable, that means you cannot solve this problem by computers. Okay, so basically they cannot solve this problem by computers. Okay, and there is a slightly different from uh, write a program to solve this problem versus you cannot write any program to solve it. So there's a slightly difference between the two. Okay, and holding problem is that you can write a program to solve it, but the program will not tell you the result. Okay, and there are some problems you cannot even write a program to solve it, and in either case they are all undecidable. So we're gonna prove this holding problem by contradiction. In other words, that there's no decidable program that will solve this problem. Okay. So the proof is, first we assume H is decidable. Decidable means that you can have a program that will eventually give you the result. Okay. So let's say this program we can call it an algorithm, basically the same thing. A. Okay. So let's say A is such a program. Okay, that you can solve the holding problem. Okay. So the A will accept two inputs, the program P itself and the input I. Okay. And the A, since we assume A is decidable, okay, so it must output 1 if P holds on I. Okay. And it must give you 0 if P does not hold on I. Okay. So note that the A must hold because we assume it is decidable. Okay. No matter what. Okay. Whether it's uh, it determines P holds on I or P does not hold on I. But P may or may not. Okay, so make sure you understand this. So based on A, we can create another program called Q, or another algorithm. Okay, and the Q now only accept one argument versus A accept one program, one input. Okay, and Q only accept just one input program P. And notice that the P is a program, I is input. So a program, if you look at the internal memory in a computer, it's a long binary string. Okay, and input I, it could be also another binary string. Okay, so basically these two inputs are binary streams. Okay, and now Q now accept just one binary string. Okay, so the Q's result or Q's behavior, okay, based on A, because A is, we assume is decidable, so A must give you answer. Okay, so if the answer A PP is 0, we give it 0, then Q will holds on P. Okay, so the Q's behaviors depends on A, the output of A. Okay, if If they say the APP, okay, is 1, okay, then Q does not hold on P. So we build P based on A, basically, okay. Now we consider we put, because P is basically a binary string, okay, and the Q is a program we created, also another binary string. So we can put Q as an input to itself. So we consider Q and then replace P with Q, okay, and the output could be one or the other, okay. So first, if the output is first one, Q holds on P. So Q holds on P, that means now we replace P with Q. So that means Q will hold on Q. Okay. Then if what? If P A, because P, now we replace that P with Q. So it's AQQ equals to 0. Okay. And now if you look at AQQ equal to 0, that means Q does not hold on Q. So Q does not hold on Q. But earlier you said Q holds on Q, and you also said Q does not hold on Q. So that's contradiction. Okay. And the other case is Q does not hold on. If Q does not hold on Q, okay, then that means AQQ must be equal to 1. If AQQ must be equal to 1, okay, that's this one. That means, Q holds on Q. But you say Q doesn't hold on Q, also Q holds on Q. That's another contradiction. So either case, uh, this is a contradiction. So we can have this assumption right. So the problem coming from the wrong assumption. Okay, that H is decidable. Okay, because H is decidable, so we can have A, but A does not exist. So H cannot be decidable. So H must be undecidable. Okay, so we can use a pictorial diagram to show this relation. So first we build a Q or program based, I can call it machine, based on A. So Q has got input P, okay, and the Q's behavior has is either holds or looping, okay, not holds, okay, does not hold. So it depends on A, and A will receive the two inputs from well, A is receiving two inputs, but now Q only got one input P, so the Q will duplicate another input to A, so A will got two inputs as well. So now A, if A is equal to 1, okay, A not A equal to 1, the output of A, okay, equal to 1, that means um, the A PP holds, okay, at that time. Then we create a loop for Q. Notice that the create a loop in the Q is a trivial, okay. You can well, you can have a while true and you keep looping, okay, it's no big deal. And now if the AQQ, okay, APP, okay, is equal to 0, then Q will hold. So simply, whenever Q determine the output of A is 0, then Q will just, jump to the end, okay, and holds. Okay, so that's explain the whole concept. And this type of pictorial diagram basically showing the reduction. Okay, so we actually create a reduction uh, from one domain to another. Okay, so that concludes this video. Hope you enjoy, and if you like, share and sum up. And thank you. Have a good day. Bye.